Hello grade 11 students. Today I am here to teach you chapter 25 in your textbook that's called probability. So we discussed this section in grade 10 as well. So we discussed about sample space, independent events, mutually exclusive events. So it's useful to watch grade 10 chapter 30 before you start this lesson. Now we'll see what are the basic concepts in probability and we'll revise certain things that you learned in grade 10. We'll take an example. Throw a six-sided die. Write down the sample space. So can you remember? We use letter S to denote the sample space, and if this is a die, six-sided die, what are the numbers you can get? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's the sample space. Find the probability of getting an odd number. So we'll say this is A. A is the set of getting odd numbers. So what are the numbers odd here? 1, 3, 5. So they are asking what's the probability of getting an odd number. So we can write P for probability, and here PA is equal to number of outcomes in A over number of outcomes in the sample space. What is NA? 1, 2, 3. Out of NS, 1, 2, 3, 4, 5, 6. So 3 over 6 we can simplify and write down half. So what's the probability of getting odd number? You get half. Now look at this one. Getting a square number. We'll assign this one as B. What are the square numbers? We can take 1. 1 squared is 1. 2 squared, you get 4. 3 squared is 9. 9 is not there. So how many observations? How many elements? 2. So what's the probability of getting a square number? 1, 2. 2 over 6. You can simplify and write 1 over 3. Now the next one, we'll assign this one as C. Getting multiple of 8. What are the multiples? 8 times 1, 8. So 8 is not there. So this is an empty set. So null set. So we can write down what is probability of NC. What is NC? NC is 0. There are no elements. So what's the probability of getting C? 0 divided by 6. We get 0. We'll take another one. 1 to 10 numbered cards are in a box. Take a card randomly. Write down the sample space. So there are 10 cards numbered 1 to 10. So what's the sample space, capital S? You have to write all the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. I'll write here. So all the numbers we have to write in sample space. Find the probability of getting prime numbers. So I'll take this one as A, capital A. What are the prime numbers? We know the smallest prime number is 2. Next, 3, 5, 7. So how many elements are there? 4. So what's the probability of getting a prime number? Number of elements in A, 1, 2, 3, 4, divide by number of elements in the sample space. That's 10. So you can simplify and write 2 over 5. getting multiples of 3. So we'll take this one as B and I'll write here what are the numbers. Multiples of 3. 3 times 1, 3. 3 times 2, 6. 3 times 3, 9. So 3, 6, 9. So what's the probability of getting B? 3 numbers are there out of 10 numbers. So 3 over 10. Getting a number less than 5. We'll take this one as C. So what are the elements? Less than 5. So you can't take 5 there. 1, 2, 3, 4. So how many numbers? 4. So what's the probability of getting C? 4 over, altogether there are n numbers, 4 over 10. So simplify and you can write 2 over 5. Now the next one, getting a number between 7 and 9. Between means 7 and 9 not included. So if this is D, what are the numbers in between 7 and 9? You get only 8. One outcome is there. So what's the probability of getting D? Is 1 out of 10. So that's how we find out the probabilities. Question number 3. This is another example. There are 3 red, 4 blue marbles in a box. A child is taking a marble randomly from the box. Write down the sample space. So here there are 3 red ones. So we can take R1, R2 and R3. What about blue ones? We can take B1, B2, B3 and B4. So in the sample space I can write R1, R2, R3 and then B1, B2, B3 and B4. Then find the probability of getting a red marble. So how many red marbles are there? So I'll take this one as A. When you take the set A, red marbles, you can get either R1, R2 or R3. So how many outcomes are there? 3 outcomes. So here, what's the probability? Probability of getting A is 3 outcomes over total number of outcomes. 1, 2, 3, 4, 5, 6, 7. So here we can write NS equals 7. So 3 over 7. Now look at this one, not getting a red marble. So not getting red marble, you can either count how many other colored marbles or what's the other method? Can you remember? The complement. If A is an event, A dash is a complement. So not a red one is A dash. So A dash is B1, B2, B3, B4. So if you want to find out the probability of not getting red marble, you can either count these and write down probability of A dash is 1, 2, 3, 4 out of 7. Or what's the other method? You can take 1 minus. So what's the equation? We did this in grade 10. PA dash is equal to 1 minus PA. So 1 minus probability of getting red marbles we did in first part. So that's 3 over 7. So here 1 I can write 7 over 7 minus 3 over 7 becomes 4 over 7. Review exercise. Question number 1. A is an event in the sample space S of a random experiment with equally likely outcomes. If NA is 23 and NS is 50, find PA. So what's the formula to find out probability of getting A? Number of elements in A over number of elements in sample space. So NA is 23, NS is 50. So the probability is 23 over 50. So what is probability of A dash? I can use the formula 1 minus probability of A. So here probability of A is 23 over 50. So I can write instead of 1, this is 50 over 50. So 50 minus 23, you get 27. So the probability is 27 over 50. Question number 2. The sample space S of a random experiment is 1, 2, 3, 4, 5, 6, 7, 8. Assuming that the outcomes of this experiment are equally likely, answer the questions given below. A is a simple event of the above experiment. Write down all the events that A could be. Simple events means only one outcome. So there are 8 numbers. So we can write down A can be 1 or 2 or 3, 4, 5, 6, 7 and 8. So only one possibility. So those are simple events. Part 2. For each of the above events, find probability of A. So what's probability of A? NA over NS. Number of elements in A over number of elements in sample space. NA, always this is 1 element. So 1 over. How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 numbers. So always the probability is 1 over 8. Part 3. B is a compound event of the above experiment consisting of 4 elements. Write one event that B could be. So only 4 elements. So you can write down any 4. 1, 2, 3, 4 or 5, 6, 7, 8 or 1, 2, 6, 7. Any 4 elements. So I'll write, they want only one event that B could be. So I can write B could be 1, 2, 3, 4. Now part 4. Find probability of B. Now we know B has 4 elements. So what's the probability of B? Number of elements in B over number of elements in the sample space. 4 over, altogether 8 numbers are there. 4 over 8, or you can simplify and write down half. Then what is probability of B dash? We know probability of B dash is 1 minus probability of B. We found out probability of B is half. This one I can write 1 as 2 over 2 minus 1 over 2. You get half for probability of B dash. Now fifth part. X is another event with Px is 0.5. Write 2 elements that X could be. Okay, so here this one 0.5. Can you write as a fraction? Px is 0.5 means, So px is 0.5. So write this as a fraction, you get half. But the total number of outcomes is 8. So you need to convert this to 8. So how can we get 8 here? You need to multiply this by 4. So 4 times 2, 8. So here you have to do the same thing to the numerator. So what's the answer? 4 times 1 is 4. So that means out of 8 elements, you can get 4 elements, any 4. So X is any event that you get only 4 elements. So what can be the elements now? It says, what are the numbers here? 1 to 8. So you can write 1 to 8, any 4. So I'll write 1, 2, 3, 4, or another one, 5, 6, 7, 8, any 4 elements. So here it says write 2 events that X could be. So here X can be either 1, 2, 3, 4 or 1, 2, 5, 6. So you can write any 4 elements. Question number 3. The following Venn diagram provides information on the number of elements in the subsets relevant to 2 events of a random experiment. Determine the following. NE. This is epsilon. Can you remember epsilon is a universal set. That means entire set. So NE. Before we write NE, we need to write down the elements in epsilon or universal set. So when you look at this one here, these are numbers. So we can't write down the elements. So I'll erase that. We can just count how many elements are there, because just a number given means number of elements there. So 12 plus 3 plus 7 plus 5 is the entire set. So 7 plus 3 is 10, 10 plus 12, 22, 22 plus 5, 27. So I'll write down how we got 27, 12 plus 3 plus 7 plus 5. Then the second part, probability of getting A. Here, when you take circle A, how many are there? So take circle A, 12 plus 3. So 12 plus 3 is the number of elements in A divided by total number. Total number is 27. So when you simplify 12 plus 3, you get 15 over 27. When you simplify, divide by 3, 5 over 3 times 9, 27. So 5 over 9 is probability of getting A. Now third part, probability of getting B. So we have to consider B circle. So when you take B circle, how many altogether? 7 plus 3, that's 10, divide by 27. You can't simplify further. Then this one, A intersection B. A intersection B is the common part, the intersecting part. So you are asked to find out the probability. So this is 3 over total number, 27. When you simplify, you get 1 over 9. Next one, A union B. A union B means everything inside the 2 circles. 12 plus 3 plus 7. So probability of getting that is, first find out the elements in all 2 circles. Here 12 plus 3 plus 7. Divide by 27. So 7 plus 3 is 10. 10 plus 12 is 22. Divide by 27. This one, A intersection B dash. So B dash means you have to cover B, but it intersects with A. So B dash intersects with A is 12. So what's the probability? 12 over 27. You can simplify and write down 3 times 4, 3 times 9. 4 over 9. Next one. A dash intersection B. A dash means you cover circle A and intersects with B. That's 7. 7 over total number is 27. So you can't simplify there. And the last part, A union B dash. Whole thing dash means outside the two circles. Outside the two circles, you get 5. 5 elements are there. So 5 over 27. Question number 4. 3 identical cards numbered from 1 to 3 are in a bag. One card is drawn out at random and the number on it is checked to see if it is odd or even. And then the card is replaced in the bag. A card is drawn out again at random from the bag and the number is similarly checked to see whether it is odd or even. Part 1. If the sample space is denoted by S, write S as a set and write down NS. So here you are taking 2 cards. So first take out of this bag once and then replace that and take another one. So you are taking 2 cards. So what are the possibilities? We can write S as 1, 1. You can get 1, 2, 1, 3, or you can get 2 with 1. So this is first time 1, second time 1, first time 1, second time 2. This means first time 2 and the second time 1. And other one, 2, 1, 2, 2, 2, 3. Then you can get 3, 1, 3, 2 and 3, 3. Those are the outcomes you can get. Part 2. If A is the event of both numbers drawn being even, write A as a set and write down NA. Here another part is there. You are asked to find out NS. So what is NS there? How many outcomes? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 outcomes are there. Now second part, A is both numbers are even. So what are the numbers even? 2. Only 2 is even. So you can write 2. 2 is the only possibility to get both even. So what's the NA value? Just 1 outcome is there. Then hence find probability of A means now we have NA and NS. So NA over NS is the probability of getting A. NA equals 1, NS equals 9. So the probability is 1 over 9. Represent S on a grid. So here, this is sample space grid you have to draw. So we can take one axis as first card. And the next one, this axis as second card. Then what are the possibilities? You can get 1, 2, 3 here. Here also 1, 2, 3. Now what are the possibilities? 1, 1, 1, 2, 1, 3. 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So that's the sample space grid. Part 5. If B is the event of drawing exactly one even number, then square the points on the grid that belongs to B and find probability of B. One even number. Now we'll see what are the numbers you are getting. If this is 1, so this one is one even number. If you take 2, this is one even number, and also this is one even number. If this is 3, 3 with 2 is one even number. So that's the B. So I can circle this one as B. So here I'll include all these. So this represent everything together is the set B. And find out probability of B. Probability of B is 4 outcomes out of 9. Part 6. Represent S in a tree diagram and find the probability of drawing at least one even number. Can you remember we did this in grade 10? So this is the sample space grid. Now they are asked to draw a tree diagram. So if you take the first card, how many outcomes are there? 3. So we draw 3 branches. 1, 2, 3. Then second card also you get 3 branches. So here we draw 1, 2, 3. 1, 2, 3 here. 1, 2, 3. So this is the tree diagram, but we need to write down the probability. So altogether 3 outcomes getting one number is 1 over 3. All these probability 1 over 3. Now we'll answer the question. Find the probability of drawing at least one even number. At least one even number. We'll try to find out at least one means you can get this branch. Or this one with this one. 2, 1. Or 2, 2 or 2, 3. At least you can get either one even number or both even numbers. Then the next one, if you take 3, 3 with 2. So you have to add all these together. So we'll see what's one branch means. When you take one branch, you multiply the probabilities. 1/3 multiplied by 1/3 is 1 over 9. So one branch represents 1 over 9. How many branches are there? 1, 2, 3, 4, 5. So the answer is 5 over 9. So that's the probability of drawing at least one even number. Now we'll see what are independent events. We did this in grade 10. If the incidence of one event does not affect the probability of the other event, events are independent. We'll take an example. Take a coin and a die, fair die. We toss the coin and the die at once. So, probability of getting head is not affecting to getting probability of any number. So, those are called independent events. Another one, take a bag with different colored marbles. You are taking one marble and observe the color. Then you are replacing it to the bag and take another one. So you get same number of marbles first time as well as the second time. So the probabilities are not changing. So those are called independent events. Now we'll see what are dependent events. If the incidence of one event does affect the probability of the other event, events are dependent. For example, think about there's a good player, cricket player in the cricket team. Absence of that team member affect the winning chance of the team. So if he gets absent, more chance to losing the team. So that's dependent. Another one, take a bag of several marbles with different colors. Take one marble from the bag and observe the color. And you are not replacing that and taking another one. What happens when you are taking from the bag? You are taking one. So earlier if there are 5 marbles, when you are taking the second one, now you have 4 marbles. So the probabilities are changing. So those are called dependent events. So when you get a problem like that, first you need to identify whether it's an independent event or dependent event. Now we'll look at this example and see whether it's independent or dependent. In a bag, there are 3 blue balls and 2 red balls of the same shape and same size. A ball is randomly drawn out and the color is noted. After replacing it, so there's this word, replacing it, a ball is randomly drawn out again and its color is also noted. Represent the sample space of this random experiment on a grid. First tell me whether it's an independent or a dependent. Taking a marble or taking a ball and then replacing it. So what do you think? It's an independent event. So we can represent this in a sample space diagram. So how many red colors are there? 2 red. We'll denote this by R1 and R2. Then 3 blues, B1, B2, B3. Okay, so here we can take the first ball this side and second ball to this side. And then 3 blues, I can label B1, B2, B3 and 2 reds, R1, R2. On the other side also same marbles, B1, B2, B3, R1 and R2. So what are the outcomes? You can get B1, 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 B2, B1, B3. These are all possible outcomes when you take 2 balls from the bag. So how many altogether? Count and see. This side 5, 5, 5 times 5, 25 altogether. And then it says, find the probability of each of the following events using the grid. The first ball being red. So I'll take this color. First, I'll put this one as A. First ball being red. So this one should be red. So you can take this set. So that's A. So what's the probability? How many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 outcomes out of altogether 25. 10 out of 25, you can simplify. 5 times 2, 5 times 5. So 2 over 5. Then the second ball being red. Second ball being red, I'll take this one as B. This is B. Second ball, this side, being red. Second ball being red means you are getting this set. So here, how many outcomes? 1, 2, 3, 4, 5. 5 times 2, 10. So what's the probability of getting B? Same thing. 10 out of 25. That's 2 over 5. Third one, part C, both balls being red. I'll take another color. Both are red. So red, red, and also these red as well. So you are getting these 4 outcomes for part C. I'll take this one as C. So what's the probability of getting C? 4 outcomes out of 25. Then part D, I'll take red color. Both balls being the same color. I'll label this as D. So what's probability of getting D? Same color. So blue with blue, this set, as well as red with red, this set as well. So all together, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 9 plus 4, 13. So 13 outcomes out of 25. And the last one, I'll take black and I'll label this is as F. We are not taking E because universal set normally we take as E. At least one ball being red. One ball being red. At least means either one ball or both balls can be red. So here if you take blue, this one you can get. And if this is red, at least means you can take one red or both red. So the whole thing comes. So what's the number? So this whole thing, this set as well as this set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 over 25. Example number 2. In Sithija's pencil box, there are 2 red pencils and 3 blue pencils of the same size and shape. Sithija randomly draws one pencil out and gives it to his friend, Thimalini. Then Sithija randomly draws another pencil out for himself. This one pencil, take it and give it to another person. Write the sample space in terms of the outcomes and then represent it on a grid. Find the probabilities. So, is this independent or dependent? Think about carefully. You are taking a pencil and give it to another person, not put it back. So, this is dependent case. So, when you are getting dependent case, when you draw the sample space grid, normally you are not getting the main diagonal term. So, we will see how we can draw. So, here this is for Thimalini. And this is, we'll take Sithija's pencil. Thimalini's pencil. So Thimalini's pencil can be 2 red ones. That means R1, R2. And 3 blues. B1, B2, B3. What about Kshitij's? Same outcomes, R1, R2, B1, B2, B3. Now what happens? Think about that Kshitija gave the red one to Thimalani. Then can you get again the same pencil? So you are not getting this one, you get all these other possibilities. When you take R2, you can't get R2 again. So you get these outcomes. B1, you can't get B1 again. B2, that means you can't take B2 again. For this one, you can't take B3 again. So can you see? So the main diagonal term is this. You are not getting those elements. Now what's the sample size? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 now. So write the sample space in terms of the outcomes and then represent it on a grid. Find the probability of each of the following events using the grid. So we'll see part A. Drawing a red pencil for Thimalani. So Thimalani is this side. So red pencil is this one. So how many outcomes? 1, 2, 3, 4, 5, 6, 7, 8 elements out of 20 elements, because without this diagonal term, NS is 20 now, because this is dependent case. So 8 over 20, or you can simplify and write down 4 times 2, 4 times 5, 2 over 5. Next one, B. B, it says Kshitija drawing a red pencil for himself. So red pencil for Kshitija. So this part you can get. So how many outcomes? 1, 2, 3, 4, 5, 6, 7, 8 out of 20. When you simplify, you get the same answer. Part C. Both getting pencils of the same color. So that means if Thimalani gets red one, Kshitija also getting red one. So here these outcomes you can get. If these are blue, you can get blue ones. So how many altogether? 1, 2, 3, 4, 5, 6, 7, 8. So 8 over 20, again divide by 4, you get 2 over 5. Now last part, I'll take a different color. I'll take black. Part D, only Thimalani getting a red pencil. That means Kshitija is getting a blue one. So these should be red and these should be blue. So altogether 6 elements are there out of 20. Simplify, you get 3 over 10. Exercise 25.1. In a box there are 2 white balls and 4 red balls of the same shape and size. One ball is drawn out randomly from this box and its color is noted. Write down the sample space of all possible equally likely outcomes. So without the diagram, first you need to write down the sample space. So 2 white balls I can take 1, W1, W2. 4 red balls I can take R1, R2, R3 and R4. Just one ball is taking. So what's the sample space? Just you can get W1, W2 or R1, R2 or R3 or R4. Just one ball is selected. Then part B. If the ball is put back into the box and ball is randomly drawn out again and its color is also noted, draw the sample space of the equally likely outcomes of this experiment on a grid. Is it independent or dependent? This is independent. You are replacing it back. So this is independent case. So we'll try to draw the sample space. So we'll take this one for part B. So here we'll take the first ball here and the second ball this side. What are the colors? W1, W2, red 1, red 2, red 3 and red 4. You are getting the same colors here. W1, W2, R1, R2, R3 and R4. So these are the possible outcomes. So you have to mark all the possible outcomes on the grid. So you are getting this. Then part C, if the ball is not put back into the box and another ball is randomly drawn out and its color is noted, draw the sample space of this experiment on a grid. Now what happens? You are not replacing the ball again. So that's dependent case. So when you are doing the dependent case, what happens? You are not getting the main diagonal terms. Second ball. So same axis. Here you can mark the same colors. W1, W2, R1, R2, R3 and R4. And if you get first time white one, you can't get white one. So the other elements are getting. Then W2, you can't get W2 again. If it's R1, you can't get R1. R2, you can't get R2. For R3, cannot get R3 again. R4, you can't get R4. So here can you see the main diagonal terms you are not getting. Now part D, for the experiments described in B and C, these two, find separately the probability of the two balls taken out being of the same color. So we'll find out for part B, same color. So that means the white with white. It can be this one. Or red with red. It can be this set. So all together, how many outcomes? 1, 2, 3, 4, 1, 2, 3, 4, 16 and 4. 20 outcomes out of how many altogether? 5, 6 here, 6 this side, 6 this side. 6 times 6, 36 outcomes. When you divide by 4, you get 5 over 9. Now look at the next one. When you are not replacing the ball, that's dependent case. How many possibilities are there? We can do 36 minus 1, 2, 3, 4, 5, 6. 36 minus 6, 30. Or you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. Always fives. 1, 2, 3, 4, 5, 6. 6 times 5, 30. So the probability, you need total number of outcomes, that's 30. Now, what's the probability of getting same color here? If this is white, this is white. And if this is red, you are getting all reds. Now the outcomes are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 outcomes out of 30. When you simplify this, you get 7 over 2 times 15. 7 over 15 for the probability. Question number 2. In a bag, there are 4 ripe mangoes and 1 raw mango, all the same size and shape. Someone randomly takes 1 mango from his bag and gives it to his friend, Rajendra. After that, someone randomly takes out a mango for himself. A grid with the sample space prepared by someone is given below. There is an error in the above sample space. Draw the correct sample space on the grid. What happens here? So after he takes a mango, he give that to Rajendra. So after that, he is not taking it back. So this is dependent case. So here he drew the sample space grid for independent case. So that's the mistake. So we can draw it again. This is Rajendra's mango and this is Saman. So what's the mistakes? You can write down. This is ripe 1, ripe 2, ripe 3 and ripe 4. And what's the other one? Raw 1. Here also same thing. Ripe 1, ripe 2, ripe 3, ripe 4 and the raw one. Now what happens? You are not getting same thing. So here only these possibilities you can get. So here you can't take these elements. Same thing again. So this is the new diagram. Using the correct sample space, find the probability of each of the following events. Both getting ripe mangoes. B1. Both getting ripe means this side with this one. So this whole set. Altogether, how many are there? 1, 2, 3, 4. 4 times 1, 2, 3, 4, 5. 20 altogether. 20 altogether. Out of that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So simplify. 4 times 3, 4 times 5. So 3 over 5. Now look at the next one. Only Rajendra getting a ripe mango. So we'll take a black color. Rajendra is this side. Only getting ripe mango. So here, if this is ripe for Rajendra, Saman will get a raw mango. So these 4. So 4 outcomes out of 20. Simplify, you get 1 over 5. Third one, only one person getting ripe mango. So if one person getting ripe mango means if Rajendra gets one ripe mango, someone is not getting, or Rajendra is not getting the ripe one means someone is getting ripe one. So altogether 4 plus 3, 7. 7 out of 20. Part C. Rajendra says that at least one person is sure to get a ripe mango. Explain with reasons whether this is true or not. At least one person is sure to get a ripe mango. So at least means either one person gets ripe or both can get ripe mangoes. So here, what's the set? I'll take another color, red, and identify. So this is, both are getting ripe mangoes. And also, at least one person means if Rajendra gets a raw one, someone can get a ripe mango. So here, raw with raw, that means you are not getting this one, so this part is okay. And here, at least one person means this whole thing you can get. So here, this is ripe one with raw means Rajendra is getting ripe one. So here, this whole set here as well as this whole set. Third part, only one person getting a ripe mango. That means if Rajendra gets ripe one, this person will get raw one. So here only one person getting a ripe mango. So here this part, so you are getting this part. Or if Rajendra gets the raw one, someone can get the ripe one. So this part. So 4 plus 4, you get 8 out of 20. Simplify and you can write 2 over 5. Now the last part. C. Rajendra says that at least one person is sure to get a ripe mango. Explain with reasons whether this is true or not. We'll find out that at least one person is sure to get ripe mango means either one person can get a ripe one or both can get ripe ones. So if this is Rajendra gets ripe one, someone also can get ripe ones as well as he can get raw one as well. Because at least one person, either one person or both. This side, if this is raw, all these are ripe ones for someone. So when you take the blue color one, you are getting everything. That's 20 out of 20. That means 1. So that means it's sure to get at least one person getting ripe mango. So here you can write down probability. At least one ripe is equal to 1. So therefore, the statement is true. So at least one person is sure to get the ripe mango. Question number 3. Sarath, who was preparing for a journey, randomly took out 2 shirts, one after the other, from a box containing 4 white shirts and 3 black shirts. So took out 2 shirts, one after the other. Is this independent or dependent? This is taking 2 shirts, one after the other means not keep it back. So this is dependent events. Represent the sample space on a grid by denoting the white shirts in the box as W1 to 3, 1 to 4 and the black shirts by B1, B2, B3. Using the grid, find the probabilities of these events. Okay, so we'll take the first shirt here and the second shirt here. What are the colors? 4 white ones and 3 black ones. This side, 4 white ones and 3 black ones, 3 black shirts. 1, 2, 3. So what are the outcomes? If you are getting white one, you can't take it again. So we can mark these elements . So B3 you can't get. You can't get these outcomes, all the other outcomes you are getting. Mark everything. So this side you can't get this one and all the others you are getting. So that's the sample space grid. Using the grid, first part it says both shirts being white. Both shirts being white, I'll take this color. So white and white, this part you can get. No, so here I miss one white color. So this whole set with both shirts white means, so here this full set you can get. So how many altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 out of how many altogether? 1, 2, 3, 4, 5, 6, 7. 7 times 7, 49 minus 1, 2, 3, 4, 5, 6, 7. Altogether 42 elements are there. So 42. So you can divide by 2, 6 over 21. You can divide by 3, 2 over 7. Part 2, only one shirt being white. I'll take black color. Only one shirt being white means first time if he wears white one, second time he wears black shirts. If he wear black ones first, he can wear white ones for the second day. So altogether how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 outcomes from 42. When you divide by 2, you get 12 over 21. Divide by 3 again, 4 over 7. third part, at least one shirt being white. I'll take red color. At least one shirt being white means either one white or both white you can get. So one white or both white. So this whole thing you can get here, both white or one white. If this is B, black, you can get this one as well. Not these ones, black with black. So how many altogether? 1, 2, 3, 4, 2, 3, 4, 5. Here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 plus 3 times 1, 2, 3, 4. 3 times 4, 12 out of 42. 24 plus 12, 36 out of 42. Divide by 6, you get 6 over 7. Question number 4. In a dish, there were 3 milk toffees, 2 orange flavored toffees and 1 tamarind flavored toffee, which were all the same size and shape. Sandaru randomly took one of these toffees and tasted it. Later, she randomly took another one and gave it to her friend Jessie. By taking into consideration the flavors of the toffees represent the relevant sample space of equally likely outcomes on a grid. So we'll first do that. Is it independent or dependent? So here she takes one and tasted it. So not keeping back. So this is dependent case. So remember that. So what are the flavors? 3 milk toffees. I'll put M1, M2, M3. And 2 orange flavored toffees. O1, O2. And 1 tambourine. So T1. This side also M1, M2, M3, O1, O2, T1. This is Jessie's toffee. And this side is Sandaru's toffee. Then what are the outcomes you can get? You can't get the same thing. So here all these other possibilities you have to mark. So how many altogether? 1, 2, 3, 4, 5, 6. 6 times 6, 36. These 6, you are not getting 1, 2, 3, 4, 5, 6. So subtract 6, you get 30 outcomes altogether. Now we'll try to find out the probabilities. Part B, using the grid, find the probability of each of the following events. B1, both getting toffees of the same flavor. I'll take black one, same flavor. If this is milk toffees, then can get milk as well. If this is orange flavor ones, can get orange ones as well. If this is tambourine one, you can't get tambourine. So altogether 1, 2, 3, 4, 5, 6, 7, 8 out of 30. Divide by 2, 4 over 15. Part 2, only one person getting a milk toffee. So one person getting milk. If Sandaru is getting a milk one, other person, Jessie, is not getting milk. So she can get other flavors. If Sandaru is getting orange ones, other person, Jessie, can get milk toffees and tamarind one. If Sandaru is getting tamarind one, Jessie can get all the other flavors. So how many altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So 22, we'll check again. Here 9, 2, 6 and 5. 20, 22. So here you are getting 22 over 30. Simplify. Divide by 2. You get 11 over 15. Then the third part, Jessie getting a tamarind flavored toffee. Jessie is getting tamarind one. So Jessie is here. So she gets only tamarind one. So this one, and Sandaru is getting other flavored toffees. So this part is the required elements. So here tamarind for Jessie and the other flavors for Sandaru. 1, 2, 3, 4, 5. So 5 out of 30. Simplify, you get 1 over 6. Now we'll see how we can solve problems using tree diagrams. So why we are drawing tree diagrams? When you get more than 2 events, but in your syllabus you are getting only up to 2 events. So here we'll see 2 event one with a tree diagram. Example number 1. In a bag there are 2 white balls and 1 black ball of the same size and shape. One ball is randomly drawn out and its color is noted after replacing it. So that means this is independent. A ball is randomly drawn out again and its color is also noted. Represent the sample space of this random experiment in a tree diagram now. So in a tree diagram you don't need to label white 1, white 2. So white color or black color. So how many parts are there? Either white or black. So what's the probability? 2 whites are there. Out of altogether, this is 2 and 1. Altogether 3 balls are there. So this becomes, if this is 2/3, what's the probability of getting black? 1/3. Then the second time you can get white or black. So this is independent, the probabilities are not changing. So 2/3, 1/3, 2/3 and 1/3. Now second part, find the probability of each of the following events using the tree diagram. Part A, drawing a white ball on both occasions. White on both occasions means this branch. So when you take one full branch, you multiply the probabilities. 2/3 into 2/3. You get 4/9. Part B, drawing a white ball on the first occasion. So white ball on the first occasion means this is white. It can be white for the second one or black. So here when you get something like this, you are taking two branches, and I'll show you a very short method as well. We'll first do separately. You can get white with white or white with black. You should be getting 2/3. Why? If this is whole branch is there, these two branches add up to 1. So finally you will end up with 2/3. So we'll check it out. 2 times 2, 4 over 9, 2 over 9. So 4 plus 2, 6 over 9. When you simplify, you get 2/3. That is part C. Drawing only one white ball. One white ball is, if this is white, you can't get a white, you can get a black. If this first time black, you can get a white one. So how many branches are there? 2 branches. So what's the first one? 2/3 into 1/3, or black with white, 1/3 into 2/3. Now find the answer. 2 over 9 plus 2 over 9. You get 4 over 9. Then part D, drawing at least one white ball. One white ball means, at least means either one white or both whites. So white with white, you can get this branch, white with black, black with white, but you can't get black with black. So here you have to add all these together. But there's a short way of doing that. So the whole thing is 1. 1 minus this branch, you get the other branches. So here, what is this branch? 1/3 into 1/3 is 1 over 9. So here I can write 9 over 9 minus 1 over 9. This is 8 over 9. Example number 2. In a bag, there are 3 red balls and 2 blue balls of the same size and shape. One ball is randomly drawn out and its color is noted. Without replacing the first ball, a second ball is randomly drawn out and its color too is noted. Is this independent or dependent? Not replacing. So this is dependent case. So here, remember, the probabilities are now going to be changed. Represent the sample space in a tree diagram. So here, first time, what are the colors you can get? Red or blue. So how many red ones are there? 3 red ones out of 5. 3 plus 2, 5. How many blue ones are there? 2 out of 5. Now what happens? The second one, you can get either red or blue. Here also red or blue. But the probabilities are now changing. Look at carefully. If you take a red one and not putting it back, altogether how many are there? All now there are 4. So the denominator becomes 4 for the second branch. Always 1 less than that. Now red one already taken. Earlier 3 red ones are there. Now 1 already taken. So how many remaining red ones now? 2. So then you can get a red one with probability 2 over 4. If this is 2 over 4, what's this probability? This is also 2 over 4, because when you add these two, you are getting 1. Now look at this branch. You have taken red one. So how many blues are there? So here I'll erase this one because you don't need extra probabilities there. So here we already completed this branch. Now we'll look at this branch. First time you have taken blue one and taking a red one. How many red ones are there initially? 3. So this becomes 3 over 4. So what is the next one? This should be 1. Now when you look at this way, already one blue one taken. So out of 2, 1 already gone. So 1 remaining. So definitely this is 1 over 4. So this is the tree diagram. Now we'll try to answer the questions. Using the tree diagram, find the probability of each of the following events. Drawing a red ball on both occasions. Red one, both occasions means red and red, this branch. So 3 over 5 times 2 over 4. You get 3 times 2, 6, or here you can simplify 1 over 2. 3 times 1, 3, 5 times 2, 10. This is part A. Part B, drawing only one red ball. So only one red ball. It can be red with black or black with red. So if you take red with black, 3 over 5 times 2 over 4. Or means addition. We have to take the second branch. Blue with red. 2 over 5 into 3 over 4. Now simplify. This is 1. We'll do without simplifying because then you get the same denominator. 3 times 2, 6. 5 times 4, 20. 3 times 2, 6. 5 times 4, 20. 6 and 6, 12 over 20. Now you can simplify. Divide by 4. 3 over 5. Part C, drawing at least one red ball. So at least means either one red ball or both red balls. So all branches you can take. So what's the easiest way to do? This branch, and this branch, except this one. So when you have one only, you can do 1 minus this branch. 2 over 5 times 1 over 4. So this is, when you simplify, you get 1 minus 1 over 10. So that means I can write 1 as 10 over 10. 10 minus 1 becomes 9. So the probability is 9 over 10. Exercise 25.2. In a box with 10 bulbs of the same type, 3 are known to be faulty. Nimal randomly draws out one bulb from the box and checks whether it is faulty. Without replacing the first bulb, he draws out another bulb and checks whether it is faulty. Represent the sample space of the above random experiment in a tree diagram. Nimal states that the events of the first bulb being faulty and the second one being faulty are dependent events, giving reasons. Explain whether this statement is true or false. Find the probability of each of the following events using the tree diagram. Both bulbs being faulty, exactly one bulb being faulty, and at least one bulb being faulty. when you read the question, first thing you need to understand, this is without replacing. So this is dependent events. So represent the above information in a tree diagram. So we'll draw a tree diagram. So 10 bulbs are there, 3 are known to be faulty. So what can be the other one? Not faulty. So we can say not faulty and faulty. 3 out of 10 are faulty, means the probability of getting faulty bulb is 3 over 10. So what's the other one? Not faulty. 7 out of 10 are not faulty. So without replacing, when you're taking the next bulb, what happens? All the probabilities are changing. Faulty and now look at carefully. Now already 1 taken means what's the total number now? 9. All these denominators are 9. Now we'll look at this one. Taken not faulty one. Taking another not faulty means we have to take 6 because already 1 taken. Then if this is 6, this becomes 3 because when you add these two, you are getting 1. This is 3 over 10, faulty one. So taking another faulty one, that means reducing by 1. So you get 2 here. That means this one is 7. So this is the full tree diagram. And here part 2, it says, Nima says that the events of the first bulb being faulty and the second one being faulty are dependent events. Is this true? This is true because not replacing the first bulb. So it's true. What's the reason? Not replacing the first bulb. So the probabilities are not the same. So probabilities are not the same. So that's the reason. Part 3, find out these probabilities. Find the probability of each of the following events using the tree diagram. Both bulbs being faulty. So what's the branch? Both bulbs being faulty means this branch. So this branch, 3 over 10 times 2 over 9. 3 times 2, 6. 10 times 9, 90. Divide by 3, you get 2 over 30. And you can divide by 2 again, 1 over 15. Next one, this is part A. Part B, exactly one bulb being faulty means what are the possibilities? Not faulty with faulty or faulty with not faulty. So here I'll take red color. So this branch or this branch you can get. So 7 over 10 times 3 over 9 plus we can take the other branch, faulty, 3 over 10 and getting not faulty one, 7 over 9. So when you multiply, this is 21 over 90 and 21 over 90, you get 42 over 90. So you can divide by 3. 14 over 30, divide this by 2 again, you get 7 over 15. Now take the part C. At least one bulb being faulty means either one bulb or both bulbs being faulty. So you can use the other method. So 1 minus not getting, so not faulty, both are not faulty. So I can do 7 over 10 times 6 over 9. So 1 minus 42 over 90, or I can write 90 minus 90 over 90. And what's the subtraction? You get 8 here. So 48 over 90, divide by 3. 16 over 30, divide by 2 again, you get 8 over 15. Question number 2. The probability of the football player A of a certain team playing in a match is 3/4. So A playing is 3/4. And then the probability of his team winning is 5 over 8. If A plays and winning is 5 over 8. A is there and winning. If he doesn't play, then his team winning or losing is equally likely. So then if A not playing, then winning is half. So winning or losing equally likely means half and half. This match is either won or lost. Find the probability of A not playing in the match. So A plays is 3/4. So what is not playing? 1 minus 3/4. I can write 4 over 4 minus 3/4. That's 1 over 4. Then second part, find the probability of A's team winning despite him not playing in the match. So not playing and winning is half. So here it says first stage, it says A's team winning is half and not playing is 1/4. So the probability is 1/4 into half. This is not playing and this is winning chance. So you get 1 over 8. Third part, represent this in a tree diagram by taking A playing in a match or not as the first stage and the team winning or losing as the second stage. So we'll take first 2 branches, A play or not play. Then the second branch you get win or lose. Then what are the probabilities? So here we found this is playing is 3/4, already given. So we found this is 1/4. A plays and winning. A plays and winning is 5 over 8. So what is this probability? Losing. A plays and losing, the remaining part 3 over 8. This part, A not playing and winning chance are equally likely. So this is half and half. Now we'll try to answer the questions. It says find the probability of A's team winning using the tree diagram. So what's the branch we have to take? Winning. Either A plays winning, or A, not playing with winning. So you get 2 branches. So this is fourth part. So you multiply the probabilities when you take one branch, 3/4 times 5/8 plus 1/4 into half. So here you get 15/32. 15, 4 times 8, 32 plus 1/8. Now we have to convert to the same denominator. So 32, when you convert to 32, this becomes 4 times 1, 4. 4 plus 15, you get 19/32 is the answer for part 4. Part 5. Part 5, giving reasons, state whether it is more advantageous or not for the team if A plays in the team. So we'll see A plays and then winning chance first. A plays, winning is 3/4 into 5/8. That's 15/32. A not plays and winning. Not plays and winning is 1/4 into half. So you get 1/8. When you convert to 32, that's 4/32. Which one is bigger? When A plays and winning chance is higher than A not playing and winning. So A is important for this team. So that means you can write down probability, this one. So 15/32 is more than 4/32. So favorable. So advantages, yeah, more advantage is there when A plays. So you can write more advantage is there when A plays. So that means he is a good player. Question number 3. In a bag, there are 4 ripe wood apples and 3 unripe wood apples of the same size and shape. Nimali randomly draws out a fruit from the bag. If it is ripe fruit, she again randomly draws out another one without replacing the first. If the first fruit is unripe, she puts it back into the bag and randomly draws out another fruit. Represent the sample space of the random experiment in a tree diagram. So first we'll do the first part. In a bag, there are ripe ones and unripe ones. So how many ripe ones are there? 4 out of 4 plus 3, 7. So unripes are 3 out of 7. So that's the first step. Then read it carefully. Nimali randomly draws out a fruit from the bag if it is ripe. If this is this branch, she again randomly draws out another one without replacing the first. So this part is dependent. So she can get again ripe one or unripe. But what happens to the denominator now? This is not replacing. So the denominator becomes 6. 1 less than 7. Then already ripe one taken. So getting another ripe one becomes 3. 4 minus 1. So what is unripe one? Altogether it's 3/6. Now read the next one. If the first fruit is unripe, she puts it back into the bag and randomly draws out another fruit. So this part is independent. So probabilities are not changing. So here ripe one 4/7, unripe one 3/7. So this part is dependent and this part is independent. Second part, from the following statements made by Nimali with reasons, state which ones are true. First part, part A, the first fruit being ripe and the second fruit being ripe are two independent events. What can you say? These two, the probabilities are not the same. So that's wrong. So you can say false. Part A is false. That's dependent. This is wrong. Not independent. So dependent events. Part B, the first fruit being unripe and the second fruit being unripe are two dependent events. So here that's also wrong. Second time put it back means this should be independent. So this is also false. This should be independent events. Third part, find the probability of each of the following events using the tree diagram, both fruits being ripe. So which branch you have to take? Both being ripe means this branch you have to take. That means 4/7 times 3/6. I can simplify first. 3 times 1, 3 times 2, 2 times 1 and 2 times 2. What's the final answer? 2/7. Then part B, second fruit being ripe. So I'll take black one. Second one ripe means first one can be anything. So this branch we can take and this branch we can take. So 4/7 times 3/6 plus. So what's the other branch? So other branch is 3/7 into 4/7. 4 times 3, 12. 12/42. Here you get 12/49. Now we can simplify this. Here 12 and 42 divided by 6, you get 2 and 7. So what's the common denominator for 7 and 49? That's 49. So 7 times 2 is 14 plus 12. You get 26/49 as the answer. Then part C, from the two fruits, only one being ripe. So what are the branches you can take? One being ripe means ripe with unripe or unripe with ripe. So you can multiply and add 4/7 into 3/6 plus 3/7 into 4/7. We can simplify this. 2 times 2, 2 times 3. This 3 get cancelled out with this 3. So you get here 2/7 and 12/49. Convert to the same denominator, that's 49. So 7 times 2, 14 plus 12, you get 26/49. 49. Question number 4. In Sirimal's cattle pound, there are 5 bulls and 15 cows. So we'll take Sirimal, 5 bulls and 15 cows. In Nathan's cattle pound, there are 2 bulls, this is Nathan, 2 bulls and 8 cows. Sirimal and Nathan agree to exchange one animal each. After Sirimal randomly selects one animal and then sends it to Nathan. Nathan randomly selects one animal and sends it to Sirimal. Draw the relevant sample space in a tree diagram. So think about Sirimal is having this one. So here for Sirimal, selecting a bull or a cow. What's the probability of selecting a bull? Selecting a bull is 5 over 20. What's the probability of selecting a cow? 15 cows are there out of 20. So this is Sirimal selecting an animal and give it to Nathan. So what happens to Nathan's side? What happens? If bull is given, what happens to the cows? What happens if bull is given to Nathan? So the number of bulls increases, so this becomes 3. But nothing happens to the cows, so it remains as 8. So we have to write down the probability. Now Nathan got altogether 11. Out of 11, 3 bulls are there. What about cows? 8 cows are there out of 11. Now think about Sirimal is giving a cow to Nathan. What happens now? So when he gives a cow, the number of cows increases. So this becomes 9, but nothing happens to number of bulls. That's 2. So same total, that's 11. Number of bulls becomes 2 over 11 and number of cows becomes 9 over 11. So this is the tree diagram and we'll try to answer the questions. Part 2, using it, find the probability of each of the following events. There being a reduction in the number of bulls in Sirimal's pound because of the exchange. How you get reduction in number of bulls? That means he is giving a bull and taking a cow. So what's the probability? Giving a bull and taking a cow. So this probability. So what's the first part? 2a, you get 5 over 20. 5 over 20 into 8 over 11. 5 times 1, 5 times 4, 4 times 1, 4 times 2. So the answer is 2 over 11. Then the next one, part B. There being an increase in the number of bulls in Sirimal's pound because of exchange. So how you get increase in number of bulls? That means giving a cow and taking a bull. Giving a cow and taking a bull. So this branch now. I'll use different colors. Now I'll take this one as this branch. So increase in bulls. So giving cow and taking a bull And this one, nothing will happen. Giving bull and taking bull, nothing will happen. So what's the probability? 15 over 20 into 2 over 11. You get 5 times 3, 5 times 4, 2 times 1, 2 times 2, 3 over 22. Third part, part C. There being no difference in the number of bulls and cows in each of the 2 pounds because of the exchange. There's no difference means giving a bull and taking a bull, or giving a cow and taking a cow. So we can take these 2 branches, taking bull and bull, or giving cow and taking a cow. So bull and bull, you get 5 over 20 into 3 over 11 plus this branch, you get 15 over 20 into 9 over 11. So what you get? Here I can simplify this one. You get 1/4. 5 times 1, here you get 3/4. 5 times 3, 5 times 4. So you can't simplify. So what's the answer? 3 over 44. And 9 times 3, 27 over 44. 27 plus 3, you get 30 over 44. When you simplify, divide by 2, you get 15 over 22. Now, third part. Now, suppose they exchange animals in a way different to that mentioned above. Suppose Sirimal and Nathan randomly take one animal from each of their pounds and go to their friend Abdul's house and exchange the cattle there and bring the exchanged cattle back to the pound. Find the probabilities of the events given in part 2 above for this random experiment. Now we'll see the next case. I'll take this side. Third part. Now suppose they exchange animals in a way different to that mentioned above. Suppose Sirimal and Nathan randomly take one animal from each of their pounds and then go to their friend Abdul's house and exchange the cattle there and bring the exchanged cattle back to the pound. Find the probabilities of the events given in part 2 above for this random experiment. Now in this case, it's mentioned already they select an animal and taken to the other house. So here what happens here? Taking an animal is independent for both of Sirimal and Nathan. So nothing will happen to the probability. So it's like the same as the initial case. So if you take Sirimal and earlier he got how many bulls? 5 bulls and how many cows? 15 cows. And when you take Nathan, initially he got 2 bulls and 8 cows. So the probabilities are not changing now. So how we draw the diagram? So when you take Sirimal, so taking a bull or a cow, selecting a bull is 5 over 20 and selecting a cow is 15 over 20. Now Nathan is also selecting cow or bull. So nothing will happen to this one. So what's the probability of selecting a bull? For Nathan, this is 2 over 10 and getting a cow is 8 over 10. So nothing will happen to the branches. So in this case also, whatever the animal, the probabilities are not changing for Nathan as well. So we have to write down this is bull, cow, same probabilities you are getting. So this is the diagram. Now we'll try to answer the questions. So in first part it says, there being a reduction in the number of bulls in cereals pound. So how can we get reduction in the number of bulls? Means giving a bull and taking a cow. So which branch we have to select? So we have to select giving a bull and taking a cow. So first part 5/20 into 8/10. So when you simplify, what you get? 5 times 1, 5 times 4, 4 times 1, 4 times 2, and then 1 and 5. So the probability is 1/5. Look at part B. There being an increase in the number of bulls in cereals pound. How can you get increase in number of bulls for cereal? That means he gives a cow and taking a bull. Gives a cow and taking a bull. This branch now. So I'll take a different color. So this branch you have to take. So what's the probability? 15/20 into 2/10. So simplify. 5 times 3, 5 times 4, 2 times 1, 2 times 5. So you get 3/20. Part C. There being no difference in the number of bulls and cows in each of the 2 pounds because of exchange. How we get no difference? Giving a cow and taking a cow back, or giving a bull and taking a bull. So you have to select 2 branches for that. I'll take black color. So that means taking a bull and giving a bull, or cow with cow. These 2 branches you have to select. So what's the probability? 5/20 into 2/10 plus 15/20 into 8/10. Now simplify this. 5 times 1, 5 times 4. So we'll simplify this one. And here 2 times 1, 2 times 5. Here also 5 times 3, 5 times 4. And 2 times 4, 2 times 5. So what's the denominator now? 5 times 4, 20. 1 times 1, 1 plus 4 times 3, 12/20. So you get 13/20. Question number 5. X and Y are 2 drugs given for the same illness which have 90% and 80% effectiveness respectively. If a person does not recover from the illness by using one of the drugs, then the other one is also given. If this 2 fails, then a surgery is done. Find the probability of the patient recovering after both drugs are given. So first thing, giving X and giving Y. So we have to think about giving X and recovering percentage is 90%. When you give Y, recovering percentage is 80%. So here, how can we draw the diagram? So here we can say giving X and recovering is 90%. Giving Y and recovering is 80%. You can't draw like that. You have to say X recovering. So I'll take this as. So if you take X recovering is 90%. So what is not recovering? Is 10%. 100 minus 90. If you take Y, recovering is 80%, but it says if a person does not recover from the illness by using one of the drugs. So here you can't draw the branch here. So already recovered. Then what happens? You are not getting another branch. If it's not recovering, you have to give the method Y. So what's the recovering from Y? That's 80%. Not recovering, then 20%, because 100 minus 80. So this is the chart. If both methods are not okay, then they are doing a surgery. First one, find the probability of the patient recovering after both drugs are given. So either this path, when X given, you are getting 90%, that's this branch, or X given and then from Y recovering is 10% into 80%. So what's the final probability? So this is, I can simplify 0, 0, 0, 0, here 0, 0. So I get 9 over 10 and 8 over 100. That means we have to multiply by 10. 10 times 9, 90. 90 plus 8, 98 over 100. So the probability of patients recovering after both drugs are given is 98 over 100. What's the second part? Find the probability of a patient having to undergo surgery. So how it happens? Both X and Y are not, because of X and Y, not recovering. So this branch. So what's the probability? 10 over 100 into 20 over 100. So you can cancel out the zeros and then 2 times 100, or simplify, you get 1 over 50. Question number 6. Information on the clerks and laborers who work in an institute is given in the following table. Find the probability of a person taken randomly from this institute being a laborer, a clerk. Okay, so here you don't need to draw a tree diagram. From the table you can find out the probabilities. A laborer. Altogether, how many? Total is 16. This is the total. And how many laborers are there? So laborers total is 3. So what's the probability for 1A? Probability of getting laborer is 3 out of 16. Part B, a clerk. How many altogether total? 13 clerks are there. So probability of clerks. Probability of clerk is 13 over 16. Now second part. A clerk and a laborer are randomly taken from this institute. Write all the relevant probabilities on the branches of a tree diagram. So we have to draw a tree diagram. So we'll first take clerk, and laborer. If this is clerk and male, what's the probability? Clerk and male. 5 out of, how many clerks are there? 30. If we take females, how many females are there? Clerk females. 8 over 30. Now we'll take laborers. Male, female, male, female. So what's the probability of getting a male laborer? 2 out of 3. Female is 1/3. So here again 2/3 and 1/3. So this is the tree diagram, and write all the relevant probabilities on the branches. Using the tree diagram, that's part B, find the probability of at least one of those chosen being male. Either one person male or both can be male. So here you have to take all branches except both females. So here we can do 1 minus getting the probability both female. So 1 minus 8/13 times 1/3. So 1 minus 8/39. I can write 39/39. So you get 31/39. Question number 7. In a box there are 2 white balls and 1 black ball of the same shape and size. From this box a ball is drawn out randomly and discarded, and then another is drawn out randomly. Find the probability of at least one of the 2 drawn balls being white. So this is dependent case because it's discarded, taking one and discarded. So when you take the first branch, getting white and black, 2 whites are there, 1 black means altogether 3 balls are there. So what's the probability of getting black one? 1/3. Now when you taking the next ball, what happens to the probabilities? Probabilities are changing. So this is first taking white and then taking another white. So here 1 white ball is taken and discarded. So taking another white, so this 2 becomes 1, and now the total amount of balls reduced by 1. So this becomes 1/2. Then here already black one is there and this becomes 2. So half is the probability. This branch means first one, black one is taken and discarded it, and taking another white one. So how many white ones are there? This is 2/2. And what happens if you take one black one and it's discarded? You are not getting another black one. So this is 0/2. Now we'll try to find out the answer for this one. At least one of the 2 drawn balls being white. At least one means either one white or both white. So you have to take all these branches except black and black. So black and black, what happens to the probability? This times this means 0. So getting black is 0. 1/3, I'll do it separately. 1/3 into 0/2. That means you are getting 0. That means what's the probability for the other part? So getting all the other ones, that means at least 1 white means 1 minus 0. So you get probability as 1. Question number 8. In box A, there are 3 blue marbles. So we'll draw box A, 3 blue, 2 red of the same shape and size. In box B, there are 4 blue marbles and 5 red marbles of the same shape and size and those in box A. A marble is drawn out randomly from A and placed in B. Then a marble is drawn out randomly from B and placed in A. Find the probability that there has been no change in the color composition of the marbles in A. So if you take the box A, what's B getting black one is 3 over 5. What's getting red one? 2 over 5. So now if the first one is black and replacing it to box B, what happens to box B? Black increases with this one. So 5 over, earlier 9 were there, now 5 over 10. So this is B. So this is black again. Then what's the probability of getting white one? Black is taken from this and black replaced. Nothing happens to the, not white, this is red. This is red, and how many reds are there? Same as before, 5 over 10. Now this branch means taking a red one and replacing red one. So what happens to the red ones? Red one increases. Earlier 5, now 6. Black ones, you are getting the same number of balls, 4 over 10. So this is the diagram. So taking a ball from box A and replacing in B. Then a marble is drawn out randomly from B and replaced in A. So this is the tree diagram. So this means giving black and taking black, giving black and taking red, giving red and taking black, and giving red and taking red. Now we'll find out the answers. Find the probability that there has been no change in the color. That means find the probability that there has been no change in the color means giving black and taking black again, or giving red and taking red again. So what are the branches? Black, black, or red, red. So the probability of no change is equal to 3 over 5 into 5 over 10, or 2 over 5 into 6 over 10. So first we'll multiply 5 times 3, 15 over 50 plus 12 over 50. You get 27 over 50 as the probability. Question number 9. In grade 11 of a certain school, there are 3 parallel classes. The number of children in these 3 classes is in the ratio, we'll say ABC, in the ratio 2 to 2 to 3. The teachers who teach mathematics to the 3 classes are ABC respectively. The principal makes the following statement based on his experience. 90% of the children in the class taught by A and 80% from B and 60% from class C will pass the forthcoming examination. Find the probability of a randomly chosen child from grade 11 passing the examination based on the above statement. So here we can say there are 3 branches, class A, class B, class C. So what's the ratio? 2 to 2 to 3 means total is 3 plus 2 plus 2. How many total parts? 7 parts. Out of 7, 2 parts for A. Out of 7, 2 parts for B. And out of 7, 3 parts for C. Then you can think about passing the exam and not passing. Passing the exam, not passing. And here also passing the exam and not passing. So passing, if the student is in A class, passing rate is 90%. 90 over, so I'll write like as a fraction 90 over 100. So what is this? Becomes 10 over 100. B class, passing rate is 80%. So this is 80 over 100 and this is 20 over 100. C class, passing rate is 60% and then the failing rate becomes 40 over 100. So this is the tree diagram. Find the probability of a randomly chosen child from grade 11 passing the examination based on the above statement. So you can select either from class A or B or C passing the examination. So you can take this branch, B with passing the exam and C with passing the exam. So the first part, probability is probability of passing the exam is equal to 2 sevens into 90 over 100 plus 2 sevens into 80 over 100 plus the other branch 3 over 7 into 60 over 100. So now simplify. So you get 700 in the denominator. All these denominators are the same. 90 times 2, 180. 80 times 2, 160. 3 times 60, 180. So when you add all these together, 100, 200, 300, 380. Then 400, 440 and 520. So 520 over 700, 0 get cancelled out and you can divide by 2. This is 35. Divide by 2 here. You get 26 over 35. Then second part. Using the above answer, evaluate the percentage of students who will pass. So this is the passing probability. So write this as a percentage. What you do? I can take this one easily. I'll take, without simplifying, I'll take 520 out of 700. How you convert a fraction to a percentage? Multiply by 100 and divide by 100 means we use this symbol. So 100 times 7, divide 520 by 7. 7 times 7, 49. And 30 remaining. 7 times 4, 28 and 2 remaining. So 2 sevens percentage. So 74 and 2 sevens as the percentage value. This is the last unit in your textbook. So before your O-level exam, make sure that you watch all grade 10 and 11 videos and definitely you will get a good grade. And I wish you all the best for your O-level exam. I'm sure definitely you will success in mathematics.